can see the circuit configuration in figure 27, and from the given current direction, okay, that is out of the source, and the source is at the lower, this is your source terminal, this is your gate terminal, and then you have your drain terminal. So drain terminal is at the higher potential as compared to the source. This is an NMOS device, a typical NMOS device that the circuit symbol is illustrating over here. So the design problem, we already have the Q point, that is, you have the specification of the IDQ. Okay, so we know what current the transistor is required to be biased. So we had this is biasing. This is a DC current, not the AC current. Okay, so we have the Q-cent or the IDQ current, the drain to source current, 0.5 milliamps, and then we have VDSQ. Okay, so we know what is this voltage, VDS, between VDS. So this is VDSQ. Okay, given these two parameters, given given VDS and given the IDQ, the idea is to meet a certain specifications. Okay, and these specifications, again, these are your current and voltage specifications. But with that, you need to choose the standard resistors as well. Okay, so you need to find what resistances you need, biasing resistances if any, and what the DC supplies should be, so that the transistor is biased so that the current and the voltage is it meets this criteria. Okay, so I mean this Q-cent point or this Q point could be in sat region, could be in non-sat region. Okay, when the transistor is conducting, well, that needs to be thought about. But you see this for the given current of 0.5 milliamps and VDS of 4 volts. We need to find the resistances. Okay, and these resistances, which are to be used in the final design, they need to be standard resistors. Standard, I mean like 4.7K, 5K, 10K. Okay, so something like that. So now what is available with us is that a transistor with a nominal parameter of, this is the electrical conduction parameter in microamp volt square Kn, which is a product of mobility and the oxide. Okay, and then you have this non-dimensional ratio of the width to the channel length of the transistor. Threshold voltage of NMOS is 1.2 volts. This transistor is available. Okay, from this information, the first thing you can do is to find the conduction parameter Kn. Okay, which is given by W by 2L into Kn prime. Okay, so that gives you the conduction parameter. Why do we need this conduction parameter? Because we need to use this to find the current. Okay, and this current is given to us. So the current, basically IDQ, given that, suppose that the transistor is in sat region. Okay, then you use the following current relationship. You have this Kn with you, and then you find what the VGS should be. Okay, so you need to find what is VGS. VDN or the threshold is given, so this is like this. Okay, we know this quantity, we know this quantity. This is to be found out. This is to be found out. Okay, so this is the threshold. And this is also known. Okay, so this is the relationship in sat region. If it is not in the sat region, then you use more complicated relationship of IV curve, which is dictated by this another expression for IV, which we have seen before. If you can go back and revert to, you see in table 3.1. So last time, so in this is the sat region for NMOS. Okay, this is the equation I've written. If it is a non-sat, use this relationship. Okay, so you will find VGS. Okay, you know what is VDN. All right, so you know what is IDQ. You know what is Kn, and VDS is also given. Okay, so these things are there. So only this quantity is to be determined, VGS, and over here as well, in both sat and non-sat regions. Okay, so the objective is again to design a MOSFET, a circuit biased with positive and negative voltages to meet a set of specifications. Specifications are the configuration is as shown in figure 27, and the design circuit is such that you need the Q current of 0.5 milliamps, and you need the biasing voltage VDS as the transistor has 4 volts. All right, and you have to come up with standard resistors to meet those these specifications of current and voltage. So that's the problem. Um, so you have both positive and negative voltage supplies over here. So let's see how we can find this RD and RS. So the first thing is, well, we have this, we found this conduction parameter as we find this as 0.25 milliamps per volt square. This is the conduction parameter. And then let's plug this in over here. Okay. So assuming the transistor is first of all biased in the SAT region, let's assume that we are proceeding in the right direction. It's not in the non-SAT. Let's use this conduction parameter in the IV equation for SAT region of NMOS device. VTN is known. Okay, KN is 0.25 milliamps. IDQ is 0.5 milliamps. So VGS can be found out from the same expression. Okay, so this VGS is over here, right? So this becomes IDQ over QN. You take this in the denominator, okay, then take the square root of that plus VT, and this is the expression. So solving this out, everything is known. So you find this VGS as 2.614 volts. Now, if you look at the circuit, one thing to note is that there is no gate current. Okay, there is never any gate current because there is no oxide. Okay, that means IG is always zero. Whether it is PMOS device and MOS, keep this fact in mind that is IG is zero. That means your IG RG over here, IG RG is zero. Okay, which is what? Which is VG. So that means your gate is grounded. Gate is at ground potential. So this VG, IG, RG is zero. This is gate potential. Then what is VGS? Okay, VGS can be found out as follows. You see, since the gate current is zero, the gate is at ground potential. The voltage at the source terminal is Vs, which is minus VGS, because I mean this is VG minus VGS. So G is at zero, then you're left with minus Vs. Okay, and we have already found this. I mean, VGS is 2.614 volts. Okay, this simply implies that your that Vs at the source of the transistor, you have a potential of minus 2.614 volts. All right, so that's what it implies. So this is your source. So value of the source resistor is then found. You see this is at zero. Okay, so the potential at Vs is at minus 2.614. So how do you find RS now? Okay, we need the biasing resistors. So that can be found out. You see, this will be Vs given the direction of current minus V negative, that is the negative supply at the source, divided by RS is your, basically this is your IDQ. Okay, so we have this IDQ with us. We know what is IDQ, that is 0.5 milliamps. We know Vs is minus 2.64 volts. Okay, this can be plugged over here. V negative is minus 5 volts. So the RS can be found out. So let's see what RS comes out. This is minus 2.614 minus plus 5 or 0.5. This is 4.77 kilo ohms. Okay, very close to a standard value that is available in the lab for you. Is 4.7 kilo ohms. That's almost a standard resistance, easily available. Okay, but anyways, so for now we have this RS. Let's go ahead and find RD. Okay, then we can figure out how much we can deviate from this IDQ and VDS so that your RS becomes 4.7. Okay, I mean for the given 0.5 milliamps, and also that if what we assumed before was the transistor is biased in the SAT region, if that is true, then in order to plug 4.7K instead of 4.77, how much we are going to deviate from IDS, that has to be found out as well. So, but first, let's find out what the drain voltage is. You see, we need this voltage drain, because then V positive minus VD. Once you found VD, this again is divided by RD. Okay, and from the Ohm's law you find this is equal to IDQ. So IDQ is known, only RD is missing over here, but first you need VD. Okay, just like we evaluated this for VS. Well, VD can be found from VDS. Okay, you have VDS with you. So what is VDS? VDS is your VD minus VS. Okay, and or VDS plus VS plus VS gives you VD. Okay, so this means that, well, numerically this means that VD is equal to VDS is 4 minus 2.614. That is the voltage at the source terminal over here. You see, this is the voltage at the source terminal. So this is about I think about 1.3 something. Okay, 1.3 volts. Yeah, 1.386 volts. So you have VD. Okay, and you find the value of the resistor RD as its expression I've written before. So you have IDQ, and from that you find RD to be 7.23 kilos, which is again you must say that close to the standard value, which is available as 7.5 kilos. But before we make the choice of 7.5K and 4.7K as our nominal resistor values, you should note that VDS is equal to 4 volts, VDSQ is 4 volts, is greater than VDS sat, which is given by the overdrive voltage, the difference between the gate source and the threshold. So that is for 1.41, which means the transistor is indeed biased in the saturation. So our assumptions were correct. Okay, it's not in a non-sat. I mean, starting with this IDQ current equation relating the voltage VGS, we were correct before. Okay, so you can use this. Since your VDS is VDSQ is beyond VDS sat, the transistor is already in the saturation. Okay, so you can use this as a linear amplifier. But I mean, but if it was not the case, then you have to go back, change the current equation. Okay, and then find the VGS back again. Okay, then from that VGS you find VS, then from VS you find RS, and then again you go on with your calculations with finding the RD and so on. But here the transistor is biased in the saturation region, so we are okay. We are pretty okay, right? Let's proceed. Now the trade-off is that the closest standard resistor available is 4.7K and RD is 7.5K. So if we have to use them instead of 7.23 and 4.7, we have to use the nominal values. So so first we have to find a gate source voltage. Okay, you see in this loop, VGS it's like VS minus ISRS minus 5 volts. So this expression is over here. It's VGS. Okay, G is 0. Okay, so you have actually VS. So VS, then ID RS. That is the same current, IDQ. But that has to be found. This is not 0.5 milliamps. Okay, let me remove this. This is not IDQ. You have to find how much ID now deviates from IDQ. Okay, so IDRS minus 5 is equal to 0. Okay, that's your KVL at here at this branch, the output branch. So at the source branch, and then since the transistor is in saturation region, you use this equation of ID and you plug it right over here. Okay, where ID is given by Kn, VGS minus VDS, and you find what VGS is. Okay, so the only unknown in this equation is your VGS. So find what VGS is, and if you do so, you'll find that VGS is 2.622 volts, and this gives from this it gives IDQ back as 0.506 milliamps or VDSQ as 3.83 volts. Now you notice that in this case the drain current has just changed to 1.2% of the design specification, which is pretty acceptable if you don't have this resistor values. Okay, so if you go for a 7.5K RD resistor at the drain and then at the source you plug a 4.7 instead of 4.77, so the only difference is very is quite an insignificant. It's 1.2% of the design specification, and that's the only trade-off. So, and the drain source voltage is within 4.25% of the design specification. So that is still acceptable. I mean, if the transistor is being used as a linear amplifier in the SAT region, well, you're not moving from the SAT region. You're not too close to. I mean, 3.83 is still much greater than 1.41, so there won't be any clipping in the output voltage waveform as an amplifier, linear amplifier. It is still greater than 1.41, so you are still in SAT region, okay, much away from the transition point or the saturation point. The comment is that it is important to keep in mind that the current into the gate terminal is zero. So in this case, there is zero voltage drop across the resistor RG, right? So there is no drop. I mean, this IG RG over here is zero, all right? So basically, your gate is grounded. Gate is grounded over here. The gate is grounded. So I mean, from this from this effect, we evaluated what VS is. I mean, VGS can be found out from the I and V equation for saturation region. Once this is found out, you know what is Vs because Vg is 0. Okay, so Vg minus Vs. I mean, Vs is simply equal to minus Vgs. All right, and from that you can proceed and find what is Rs. Okay, you have the same specification of the drain current that goes into the source, and so you use that to find RD as well. From VDS you find what is VD, and then you find what is the resistance RD. So that's your design. I mean, you were required to find what RD and RS are. Okay, and if the design choices are as such, you have to make that RD RS are commonly or easily available. Well, then you specify how much you deviate from the design. So the deviation is small. That's still acceptable. 1.2%. 4.25% for the drain source voltage, 1.2% for the drain current. So the design point is that in an actual design of the circuit using discrete elements, we need to choose the standard resistor values that are closest to the design values. In addition, the discrete resistors have tolerances. They always have tolerances, okay? These thin film resistors. So that needs to be taken into account. So again, there will be some more tolerance or some more deviation, but again, it won't be like 10% or over here, it won't be like, it won't be much of significant problem. But you have to take the tolerances into account. So in the final design, then again, the actual drain current and drain to source voltage, VDS and ID, are somewhat different from the specified value. So in many applications, this slight deviation from specified value will not cause a problem. I mean, you're still much away from VDS SAT, so your transistor is still in the SAT region. That's not a problem. Okay, even if you go for the standard resistor values. Okay? That's all.